Okay, so take a look at that real quick. Exam 3 is scheduled for Thursday, right, of next week, so a week from today, right? That's, exam, grab one of those copies right off that corner. You ready for the test, right? Yeah. Exam 3 next Thursday. And do you remember I told you that I might have a conflict? It looks like I'm going to be okay, so sorry. We're going to have it on Thursday. This is the review for it, okay? So it says here that for this exam I will allow you to have a reference sheet that is at one 8.5 by 11 sheet of paper, front and back. You can put any formulas, steps, procedures, anything you want on there except worked out problems. You can't just do all these review problems and call that your reference sheet. I will walk around and check those when I give the test. I expect for you to follow the steps I taught in class when you sketch these functions. So not just using like a graphing calculator and showing me what your calculator drew. All right, you're going to need to go through the steps. So what I did is I kind of gave you a sample of each kind of type of problem. So the first 3 problems are polynomial functions. So those have their own set of steps. 4, 5, and 6 are rational functions. We covered a bunch of those last class and the class before. And then we have not talked about exponentials, and we have not talked about numbers 9 and 10, which have to do with exponentials. So that's where we are, okay? Were there any questions? The video of last class I just posted this morning, so just actually like an hour ago. So it should be there now, and we're going to continue talking about exponential functions. I got a little carried away with the, what was that, the tournament, NCAA tournament last class. So let's continue talking. I showed you the bacteria problem. Remember the bacteria? I'll just remind you, we had this bacteria problem where we had one bacteria and we said that every day it would triple, right? You should have that. Every day it tripled. And so what we did is we made a table where we said this was the days and this was the number of bacteria. And we said at day 0 there was 1, at day 1 there was 3, at day 2 there was 9, at day 3 there's 27. And then we continued that pattern and we said, you know what? We could come up with a function, and we said the function would be 3 raised to the x. And that was the first time we had seen what we call an exponential function. So we talked about that. Now I want to give you another example, okay? A different example. And this one I'm going to call the folded paper problem. Folded paper problem. Remember that the things I'm showing you here are just to motivate the idea of exponential functions, right? So I have a piece of paper here. Would we all agree this is a rectangle, right? I have not folded it, right? I have not folded it, and you see one rectangle, right? One rectangle. So I'm going to make a table here. This is going to be the folds, number of folds, and then the number of rectangles that you see, okay? So no folds, one rectangle. If I fold it one time, I make a crease out of it, and crease it down the center, and then I'll kind of, this will help you maybe see the crease a little bit. If I open that up, two rectangles, right? So one fold, 2 rectangles. Okay, so now let me do it again. Fold, fold again, fold in half. I'm going to open it up. How many am I going to see? How many rectangles? 4, you think? Let's see. 2, let's see, 4. Come on. Yeah? 4 rectangles? How about if I go a third time? 8. What's the other thing you might think? Is there another number you're thinking? No? 6? Sometimes students say 6. Like it's gone like 2, 4, maybe 6 this time. but 8's what I'm hearing. Let's see, 3 folds. So let me do my third fold and open it up. Can you all see it? Oh, can you all see it? You got 1, 2, 3, 4, 5, 6, 7, 8. 8 rectangles now. Okay, what do you think on the next fold? 16? Y'all see a pattern here? What's happening? What's happening? By 2. Each time it's doubling, right? It's doubling each time. So here it is. 1, 2, 3, 4, and then 1, 2, 3, 4. So 4 this way, 4 this way. 4 times 4 is 16. So we have 16 rectangles. So again, the pattern is that each time you go from here to here, you're doubling times 2, times 2, times 2. Over here with the bacteria, it was times 3, times 3, times 3, right? And because it was times 3 each time, the function was 3 to the x. So what do you think this function is going to be? 2 to the x. Exactly. This function will be 2 to the x. Now, another way that you can see that is if you rewrite all of these as powers of 2, this is 2 to the first power, this is 2 squared, this is 2 cubed, this is 2 to the fourth, and the power matches the number being plugged in, right? So what we're saying really is that if you plug x in here, then you're going to wind up doing 2 raised to the x over here. Is this making sense or no? Yes? Yes? Any questions? So this is another example of an exponential function. So if I were to ask you right now, if I could fold this 13 times, how many rectangles would I have? Well, what are you going to need for that? Something I asked you to bring today. So we need to know how to type this into our calculator. We're going to be doing 2 raised to the 13th power. So if you have your calculator, which I hope you do, what is it? 8,192. 8,192 rectangles. If I could fold it 13 times. Do you think I can fold it 13 times? Let's see. 1, 2, 3, 4, 5, 5. No way. 6. I think that's about as far as I'm going to get with this. 6. I won't be able to do 7. Yeah. So have you ever heard of a show called Mythbusters? It used to be on Discovery Channel. There's an episode on Mythbusters where they're trying to figure out, there's a myth that you can't fold a piece of paper more than 13 times. So they got this really thin like paper that was almost like, you know, paper out of like a Bible. You know, Bibles use real thin paper. It's like really thin piece of paper. It was huge. It like took up like maybe like 2 or 3 of these classrooms. And they laid it out in an aircraft hangar and they folded it and folded it. And they got a steamroller and actually steamrolled it to flatten it out. And I think they got to 13. I'm not sure. But then they couldn't go any further. Okay? I don't remember the episode. But physically, there's a restriction on what you can do. Okay? And I like to think of it this way. If I fold it, well, let's do it this way. If I don't fold it, this 1 is how many rectangles I have, right? But isn't that also how thick this paper is? Like it's just 1 page thick. If I fold it once, right? Now it's 2 pages thick. If I fold it 3 times, it's 4 pages thick. 8, 16, 32. If I could fold it 13 times, how thick would it be? That's how thick. Well, I mean, I don't think I have a ream of paper in here, but y'all know what a ream of paper is, right? It's like when you go and you go to Office Max or something, you buy that bundle of paper. That's called a ream of paper. I think that's 500 sheets, and it's about that thick. 8,000. That's 16 reams of paper thick. That's about like this thick, right? Like maybe if I stack 16 of them up, right? Or yeah, something like that. There's no way this paper can become that thick. This paper isn't even that big, right? I mean, like how is it supposed to become? Does that make sense? So there's a physical limitation on how much we could do, but there's a mathematical number for each of these, right? If you could fold it 20 times, you know how many rectangles would be there, right? Okay, so this is our second example of an exponential function. I'm going to give you one more. The next one is the half a paper. I'm just going to call this the half a paper example. All right, so I'm going to start with a fresh sheet of paper here. And let's just say for demonstration that the distance from one end to the other is 1 foot. I know it's not, but let's just act like that's 1 foot, okay? I'm going to make a column here. This is going to be the number of cuts I'm going to make, and this is going to be the size of the paper. Okay, so right now I have not cut this. I'm about to cut this, all right? I have not cut it. How wide is it? 1 foot. I'm just going to put no cuts, 1 foot. Okay? Now I'm going to cut it perfectly with scissors right down the center. Close enough. Okay? Throw this one away. Now how wide is this? Half a foot, 6 inches. I'm going to say half a foot. So one cut, half a foot. Now I'm going to do that again. How much is here? How wide is this now? It's a quarter. It's half of a half, right? If you take half of half, you get 1/4. So 2 cuts, 1/4. Do it again. Three cuts. You do half of a fourth, right? Half of a fourth. Half of a fourth is an eighth. Do y'all see a pattern here? What am I doing as I go from one to the other? Like here I was doubling each time, right? Here we're doing what each time? Halving it, right? We're halving it each time. So to jump from one to the other, you have to basically multiply by a half to go from here to here. Multiply by a half. Multiply by a half. So what do you think the function should be here then? 1/2. No, not squared. What is it? This one, it doubles each time, so it was 2 raised to the x, right? The bacteria was 3 raised to the x. This one will be 1/2 raised to the x. You were just missing that part, okay? So the x is the number of cuts. So on your calculator, see if you can tell me what would happen if I cut that thing 6 times. So the question is, how do you type this into your calculator? How do you type in 1/2 to the x? On this calculator that I have, which is recommended for this class, I'm going to put parenthesis 1 divided by 2, and then I'm going to do my caret key, and then I'm going to do 6. That's where I'm going to type it in. Parenthesis 1 divided by 2, close parenthesis, raised to the 6th, and someone want to tell me what they get? 0.0152625, something like that. Can you all see a pattern in what's happening to these numbers? Are they getting bigger or smaller? Smaller and smaller and smaller, aren't they? If I cut this 100 times, right? If I would have done that and cut this 100 times, right? I would have this really, really small piece, right? You would have to do 1/2 to the 100th power, which will be almost nothing, but it's not completely zero, right? It's not completely gone. That's very different. What happened here is very different than what happened here. With 2 to the x, what happened was these got bigger, right? And with this 1/2 to the x, they get smaller. But notice they never go away. It would never completely go away here. If you don't believe it, do 1/2 to the 100th power. Well, I don't know. That might give you 0. The calculator has limits. No, my calculator says 7.8886 and then some other numbers. Then it says at the end times 10 to the negative 31, which means I'm going to take that decimal point and move it 31 places that way, which means I'm going to have like 30 zeros in front of this, which is an extremely small number.
If you put in 10,000, my calculator says 0.
It does?
Yeah.
Oh, if you try and put 10,000 here? Yeah, your calculator will at some point give up and say, you know what, that's so small I don't know what to do other than tell you it's 0. But technically, like officially, it's not 0. It's just infinitesimally small. Did we ever have that happen? What function have we studied where we had something like that happen, where it got really close to something but never got there? The rational functions, right? We had an asymptote. Guess what? We're going to have asymptotes here, all right? So this is just to motivate the idea. I've given you 3 examples of exponential functions. 2 of them got bigger as you plugged in bigger numbers here. These got bigger. And this example, as you plug bigger numbers in here, this got smaller. All right? So now I'm going to officially put up here what an exponential function is. I'm going to define it. And then we're going to try and graph some of them. Okay, so exponential functions. Can I go off topic for just a moment? Just for a moment. This table over here, back on this example, if I would have continued this table, what would the next number have been? Remember, we're doubling each time. 32, what would have come after that? 64 after that. 128 after that. 256. Let's go again. 512. Okay, let's stop there. Does anybody recognize these numbers? 32, 64, 128, 256, 512. Do y'all recognize those somewhere in your real life? Anywhere have you seen those numbers? What's that?
Yes, but I can't remember where.
Can't remember where? These aren't perfect squares. They're all powers of 2, though, aren't they? I mean, we know these are all powers of 2. This is 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th. Do any of y'all have one of these? What is it? We all have cell phones, right? When you buy your cell phone, right, don't they always give you an option of how much memory? Storage, right? Isn't it always like 128 gig or 256 gig, right? Do y'all recognize those numbers now? Okay, it's not a coincidence. There's a reason why there are these numbers, right? They never offer you a phone with 150 gig, right? It's always 128, 256, 512, right? So the reason why is because when it comes to a computer, which your phone is essentially a computer only knows 2 things, right? I can illustrate it very easily. Your computer, your phone, only knows off, on. That's all it knows. Off, on. That's it. That's the way everything we work with that's electronic is just a signal. It's either the signal is there or it's not there. There are 2 conditions, 2 states that it can ever be in. And so mathematically what we do is we say, well, we'll say if there's no electrical signal, we'll say that's a 0. And if there is an electrical signal, we'll say it's a 1. And so everything is based on 2 numbers only, 0s and 1s. That's the way computers understand things, 0s or 1s. 2 things are possible. 2. So everything is in powers of 2, no matter what in a computer. Everything is in powers of 2, because there's only 2 options, 0 and 1. So that means all memory, memory, whether it be your RAM or your storage, it all has to be in powers of 2 when they offer you, bigger sizes. Everything's got to be. Does that make sense? That's why. Off topic, but now you know. It's based on 2 to the x. All right, exponential function. What is an exponential function? Here's what an exponential function looks like. So we finally have gotten down to what do all exponential functions look like? They look like this. It's some number a raised to the x. That's it. In this problem, it was 2 to the x, right? In the bacteria problem, it was 3 to the x. In the tearing of the paper, it was 1/2 to the x. So I have to tell you a little bit about this number down here. There are some conditions on it. The a must be greater than 0. Okay? You're not allowed to plug a negative in here. If you plug a negative in here down on the bottom, then it's no longer an exponential function. Also, a can't be 1. And the reason it can't be 1 is because if I put a 1 here, 1 raised to any power is still 1, right? 1 squared is 1, 1 cubed is 1. Nothing happens, it just stays 1. It's not interesting, so we throw it out. But if your number is anything else, then you're going to have some sort of exponential function. So that's the condition here. A is called the base of the exponential function. We call that the base. So this would be a base 2 exponential function. The bacteria would have been a base 3 exponential function. And then the tearing of the paper would have been a base 1/2 exponential function. Don't confuse that if you're taking any chemistry classes. When I say base, this has nothing to do with acid and base. It's just base meaning the bottom. Okay, it's the bottom of the exponential function. Okay, that's it. That's what an exponential function is. Nothing more to it. So let's practice seeing if we can graph one of these. All right. So I want us to sketch. Let's do the 2 to the x. That's kind of like the classic example. I want us to draw this graph. So, you know, your test, who did not get a review? I think I actually destroyed, sorry. Someone's gonna have to take a folded one. So, you know, that's a review for the exam that's next Thursday. Y'all both don't? You know what, maybe you can like let her take a picture of that, you know? Can y'all, I'll let y'all have this one as well, but take a picture. Okay, so remember that when we were graphing polynomials, there's a whole set of steps. Graphing rationals, all these steps, vertical, horizontal, all that junk, right? I promised you last time that sketching these would be the easiest of all. And the way we're going to do it is we're just going to make a t-table, like way back old school. We're going to go make a table. We're going to plug in x, and then here f of x. So we're just going to plug some numbers in and see what comes out and then plot them. That's all we're going to do. So let's figure out what numbers we're going to plug in. And for this part, we're all going to do the same numbers. That way we all get the same picture. So what I would like for you to do is I'd like for you to plug 0 in. I want you to plug in 1, 2, and 3. I also want you to plug in -1, -2, and -3. So everyone's going to plug 7 numbers into that function to graph it. And that's all you have to do. So what do I mean by plug in? Get your calculator out, right? If you need it, you might need it. Each one of these, this means 2 to the -3. This means 2 to the -2. This means 2 to the -1. 2 to the 0, 2 to the 1, 2 squared, 2 cubed. Do you understand what I'm doing? I'm going to go ahead and do the ones I know. I don't have to have a calculator for this. This right here is 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4, and 2 cubed is 8. Anybody have like a really good PC at home, like maybe like a gaming computer or anything, or a gaming laptop? No? Okay. All right, you should get for this one 0.5. This one 0.25. Is anyone having trouble getting 0.5 and 0.25 on this? What's this one? 0.125? So what we want to do is we want to look at these as being points, okay? This is the input, this is the output. So for this, I can look at it as being the point -3 goes in, 0.125 comes out. This one is like -2 goes in, 0.25 comes out. This one is like -1 goes in, 0.5 comes out. Understand? 0 goes in, 1 comes out. 1 goes in, 2 comes out. 2 goes in, 4 comes out. 3 goes in, 8 comes out. So I have 1, 2, 3, 4, 5, 6, 7 points. I'm going to draw them on an X and Y graph, connect the dots, I'm done. All right? You'd rather do this than do a rational function, yes? No, okay. All right, so when you do this, here's a way I want you to kind of think about drawing this. Your x-axis is your inputs, right? And those are going to go from -3 to 3. That will always be the same on all the graphs we draw. Okay, you'll go from -3 to 3. The question is, on the y-axis, how far up should I go? How far down should I go? So look at all the y values that we have here. Right? Look at all these y values. What's the biggest y value I get? 8, right? So I need to make sure I go up 8. And the smallest y value I get is 0.125, which is just, a small number, but it's positive, right? It's a positive number. So when I draw this, I really only need to go up to 8. That would make that about 4, 2, 6. So let's do this. I'm actually going to start, when I draw this, I'm actually going to start with the points that I think are easy for me to put on here. Like this one right here is easy, 0, 1, right? That means I don't move left or right, I just go up 1. So that would mean this point right there. When I plug in 1, I should get 2. So I go to the right 1, up 2. When I plug in 2, I should get 4, so I go to the right 2, I go up 4. And I go to the right 3, I go up 8. What would continue to happen if I went, 4, I would get 16, right? 5, I would get 32. So it's taken off, right? It's like whew, going. So this graph so far looks like it goes like this and just takes off, right? Grows very quickly. Now if we go the other direction, -1, we're at 0.5. So -1, I only want to go up halfway. And then I go to -2, and I want to go even smaller, right? 0.25, which is even closer to the x-axis. And then at -3, I'm even closer. But we talked about this. What's going to happen as you keep on going? Are you ever going to get to 0? No. So this would be a good time for me to put a dotted line. That's actually not part of my graph. This is a horizontal asymptote. And when I draw this, my graph is going to get closer and closer to it without actually ever touching it. And everybody, this is the graph of the exponential function with base 2. Okay? So if we were looking at this graph, this is not a line, right? This is not a line. This is not a parabola. Parabolas go like that. It's not a polynomial. Polynomials go like this, right? And then left and right do that. It's not a rational function. It may look like one, but it's not. Remember, rational functions, vertical asymptotes, this is not a vertical asymptote. This keeps going and keeps going up and to the right. Now, it does have a horizontal asymptote, but it's not a rational function. The rate at which it grows is just different than a rational function. So this is what we would call exponential growth. And the way you think about it is if you were to read this like a book from left to right, it's growing, right? It's growing. Not all exponential functions, not all of them are growth. Some of them do the opposite of this. As you go from left to right, they go down. and that's called decay. And let's do an example of that, all right? So let's just take, I'm going to do a completely different example, something we haven't looked at. Let's sketch the function f of x equals, what's the one on the review? Let me see, I just want to make sure I don't accidentally do that one. Yeah, okay. So let's go 0.27 to the x. So my first question to you is this an exponential function? Is it some number raised to the x? Yes. Is that number positive? Yes. Is it 1? No. Okay, so it can be an exponential function, right? You just got to make sure this number has to be positive and it can't be 1. So I should be able to graph this. Now, when I do this, I'm going to have to use my calculator. Question?
Is decay only possible whenever it's less than 1?
What do you think? Does that seem to be the case? Kind of, exactly. And I'm going to put that, I'm actually going to put that on the board, but it was going to be after I do the example. But you've seen that before, which is good. This is going to be decay. This is going to be the opposite of that. But let's convince ourselves with a table. So nice observation. So we have x here. This is our function. The numbers we said we all agree we're going to plug in are these. Everybody got their calculators ready? You're going to be doing 0.27 raised to the negative 3. You're going to go 0.27 raised to the negative 2, 0.27 raised to the negative 1, 0.27 to the 0, 0.27 to the first power, 0.27 to the second power, and 0. When I was in middle school, one of our English teachers died in front of the class. I wasn't in that English class. It was one of the other classes, but it was terrible. Everyone was traumatized. She just like fell over. Boom, gone. I'm just choking on my soda, that's all. All right. Who wants to tell me what you get there? Anyone? Anyone? 50.8. Good. So look, everyone here, you need to make sure you can get this on your calculator. If you can't, or you're having trouble, this is the time to ask. Everyone good? I can come over there and help you.